Hello everyone, I'm Yang Bai. Today I'm going to present our paper called SPiDR, Ultra-Low Power Acoustic Spatial Sensing for Micro-Robot Navigation. This is a joint work with my colleague Nakul Garg and my advisor Nirupam Roy. We are from the University of Maryland, College Park. Tiny robots become more and more promising in the last several years. They have a lot of functionalities. They not only can walk, they can also fly as insects, navigate through apertures, take turns, and so on. These tiny robots, if combined with automatic navigation, can create a lot of new possibilities in a wide range of applications. They can revolutionize the way we do farming. They can also enable autonomous exploration in deep sea where humans cannot go. They can be the first responder of disaster management and rescue, and many more applications are possible if these tiny robots are paired with autonomous navigation. However, these tiny robots are still far from applying to real-world scenario because they still have a lot of bottlenecks, such as locomotion, navigation, and communication. One of the key challenges is the sensor for navigation. You may feel confused here because the navigation problem for autonomous driving cars has almost been solved. These cars can even navigate in a busy road. However, these existing techniques are not applicable on tiny robots because they are too power hungry. LiDAR consumes tens watts of power to create 3D map. Radar also consumes watts of power because they require an array of sensors to transmit signals simultaneously. Depth camera also consumes watts of power. We can see this autonomous driving car is built in a super powerful battery, but this tiny robot only built in with 25 milliamp hour battery. Let's first take a look at the power consumption breakdown of this tiny robot. The total power consumption of the tiny robot is around 300 to 400 milliwatts. And the most power consuming part on this tiny robot is the actuators. They consume almost 60% of the power. And within the remaining power, only 10 to 30 milliwatts can be applied on sensing and computation. So here, we challenge ourselves a question. Can we enable ultra-low power navigation for tiny robots? And the navigation sensor should also fit in the size of only a few centimeters. And the answer is yes. Our system consumes only 10 milliwatts of power with one pair of speaker and microphone. First, let's take a look at this cross-sectional depth map. Basically, what navigation sensors do is they create cross-sectional depth map to find out where the obstacles in the scene. And what traditional navigation sensors do is basically they scan the scene angle by angle and find out which direction the reflection signal is coming from. One of the scanning is mechanical scanning. We can see that the mechanical scanning is very power consuming because it requires the motor to keep rotating the transducers. Another kind of scanning is beamforming. Well, beamforming does not require a motor, but it requires an array of transducers to keep transmitting the signal simultaneously. And it requires a complex hardware pipeline and processing requiring resulting to a high power budget and computation complexity. So scanning fundamentally adds a power barrier. Our approach to achieve a low power, small size, and lightweight navigation solution is we break away from the scanning approach. We developed we call a system called SPiDR, a navigation solution for ultra-low power tiny robots. This is our core intuition. We call it coded signal projection. Let's first review what is the signal propagation process in real world. When the ultrasound speaker starts transmitting the signal, it propagates to omnidirection. So if there are two objects in the scene, there is no way for us to separate which angle the reflection signal is coming from. And our plan is to transmit direction-coded signal. So the reflected signal from the objects will also encode the direction information. If we can successfully unravel the reflected signals, there is a chance we can find out the direction the reflected signal is coming from and how far the objects are. And these are the informations we need for navigation. So next question is, how can we project direction-coded signal? A natural idea is we have a transducer array, and for each transducer, we have a specific phase delay. So in this scene, we will create a controlled multipath. So for each pixel in the object plane, the received signal will be unique. However, similar to beamforming approach, this approach is also power consuming because it needs a sensor array. Our solution is we develop an acoustic microstructure for code projection. This is an internal view of the stencil. When the ultrasound speakers start transmitting signal, since there are many paths inside the stencil, and the path lengths are not the same. So when the signal starts propagating through the passes, they will induce different phase delay. And these signals propagate out of the stencil will act as a emulated transducer array. They will create a controlled multipath in the scene. And in the object plane, we will have unique pattern of the received signals in each location. This is an example of the 3D model for acoustic structure. And of course, we need a very complex internal structure to induce enough diversity. What we did was we used a helical structure to diversify the signal. And an interesting fact is this acoustic structure consumes zero power because it's just a 3D printed metastructure. And, but it can have the same performance as a 10-element array. The core idea is here is the controlled multipath in space. When there is without stencil, we can see that in different directions, the signal propagated is almost the same. But with stencil, the energy has been diversified in the whole region of the scene. And if we take a look at the cross-section of the imaging plane, we can see that in different directions, the amplitude of the pattern of the amplitude in different directions are not the same. So in this way, we project direction-coded signal. And the next question is, how can we reconstruct the scene? Since we only have one microphone, so the received signal is an array of the time domain signal. And this received signal includes all the reflected signals from the scene. So we can express it as a channel matrix H times a vector of X. In the channel matrix H, each column is the received signal from the one-time calibration when we put the objects at different locations. And the vector X represents the scene, if there is an object at each location or not. And we take a look at this equation. Since the received signal and the channel matrix are known, so we can calculate the scene of the tiny robot X as the inversion of the channel matrix H times with the received signal. We used a compressed sensing algorithm called least absolute deviation to solve this equation. Until here, we can construct the scene of the tiny robot, but the problem is, since this H matrix is big, it can possibly be very computationally heavy. And the size of this H matrix depends on how big the scene is and how fine the resolution is. So here we come up with a low power scene reconstruction algorithm. Instead of inversing the whole H matrix at the same time, we first have a H meta that includes some of the components in the whole H matrix to find out the area of interest. And then we come up with a smaller but denser H matrix to increase the resolution of the scene. Until here, we achieved low power scene reconstruction. We still come up with some practical improvements to further improve the imaging performance. One way is frequency stacking. The way we make the scene more robust is we can take several snapshots at the same location with the same microstructure but different channel matrix. You may feel it is impossible because the structure is just static. But what if we transmit different frequencies? And even though the lengths of the pipes are the same, but if we transmit different frequencies, the phase difference will also be different for those frequencies. If we transmit frequency F1, the amplitude can be depressed, but if we transmit frequency F2, then the amplitude will get enlarged. And so far, we haven't considered the movement of the robot. Since during the navigation of the robot, it will capture continuous snapshots during the movement. And since these snapshots are in sequential, there will be a common place of the scene that is common in the sequential snapshots. So we reorient these snapshots, superimpose them to create a robust scene. We can see that after motion stacking, the scene becomes very clear. Here, I will talk about the evaluation. We evaluate the power consumption and the accuracy between LiDAR, distance sensor with servo motor, and SPiDR prototype. The x-axis is the accuracy, and the y-axis is the energy consumption. If we compare LiDAR and SPiDR, we can see that the accuracy is comparable, but the power consumption of SPiDR is 400 times less than LiDAR. And the accuracy of SPiDR is much higher than the distance sensor with servo motor, but the power consumption of SPiDR is still 300 times less. Here we evaluate our performance when, see if we can detect the open space between two blocks, and the result is quite promising. Here we test if SPiDR is sensitive to the depth, and we can see that when the depth becomes larger, we can also capture the depth difference. We evaluate the performance of motion stacking and frequency stacking, and the raw output is super blurred, but after motion and frequency stacking, the result has already been exactly matched with the ground truth. These are some real-world scenes. We can see the contour is exactly matched with the output from SPiDR. And we also evaluate the power consumption of SPiDR in detail. The total power energy consumption for conducting one image is 0.83 millijoules. And an interesting fact is during sampling, the power consumption is much higher than the computation. This is because the power consumption of microphone is very high, like 30 milliwatts. So we only power up the microphone during sampling to further decrease the power consumption. As a takeaway, SPiDR is a practical system for ultra-low power acoustic scene reconstruction using passive microstructures. And this acoustic structure can also be applied in some other low power sensing applications, such as hand gesture recognition and on-body sensing. And if we can achieve low power for this application, they can be paired with a battery-free system through harvesting energy in the environment. Okay, thank you. I'm happy to take questions.